I can kick us off. This is Priyanka and Aditya will be talking about the AnimateDiff. We'll be reading about a paper which is called AnimateDiff. This model talks about a novel approach of animating text to image diffusion models. In this presentation, we'll talk about the overview, we'll show a little demo, and then we'll talk about what we learned. Moving on to the next slide. Um, Aditya, do you want to go to the next slide? So, little bit overview about the problem. Uh, this paper is called Animate Your Personalized Text to Image Diffusion Models Without Specific Tuning. So the problem foundation here is, next slide, please. So the problem foundation here is we have these personalized text to image collections, and this paper talks about introducing a unit or doing a lightweight personalization for these text to image models using DreamBooth or LoRA, and then it introduces a modeling module which then generates the personalized animation generators. So if you look at the images on the right, they are the images from the animation generator. Our current text to image model, they just generate one image, but this module, motion modeling module, it enables our existing text to image models like Stable Diffusion model to generate this animation. Moving on to the next slide. So let's talk about the problem formulation. The currently existing text to video models propose incorporating temporal modeling into the text to image model itself and then tuning on large video data sets. But they have limitations on user end. The first limitation is it's highly sensitive to the hyperparameter tuning. Secondly, there's very high cost of on a user to have a personalized video collection, and then it also requires intensive computer resources to train on that personalized video collection. This novel approach, the AnimateDiff, it introduces a motion modeling module in a base text to image model, and then it fine tunes on the large video clip. So the training happens only once. The parameters of base text to image model remain untouched. And lastly, it manages to animate text to image models without further efforts in additional data collection on user end or requiring any customized training. Moving on to the next slide. This is the pipeline of AnimateDiff approach that they've spoken about in the paper. Given we have a base text to image model, for example, Stable Diffusion model, it first trains a motion modeling module on a video dataset, on a large video dataset to encourage it to distill motion priors. Only the parameters of motion module are updated, and the parameters of our stable diffusion model or text to image model remain untouched. Secondly, at interference, the once trained motion module can turn personalized text to image model into an animation generator. Moving on to the next slide.
Yeah, so the main thing that the authors have come up in their paper is the motion modeling module, and so they incorporate this motion modeling module into the approach at resolution level. So basically, you have the pre-trained image layers of the base T2I, which is nothing but the stable diffusion model in this case in the training phase. So by pre-training image layers, I mean resolution levels. So let's say this we consider this unit, and we have resolution levels like this is let's suppose this is 512 by 512 level. This is 256 by 256 resolution level, and they have these pre-trained image layers, and they are frozen basically. They do not update the parameters for these layers. But all they do is update their own modules parameters in the process. So and these motion modules are inserted between resolution levels. So between the first and second resolution level, they will insert a motion module there, and so on. They will insert motion modules along like between all the other resolution levels, and they basically perform something called network inflation. which they say that is which they say is necessary to make it compatible with to make the stable diffusion model compatible with the motion modeling module. And the way that they do is by reshaping. So you can see that the input to the stable diffusion pre-trained layers will be batch into channels, into frames, into height, into width, and they do reshaping of the frame axis. So basically, they'll combine the height and width axis with the batch axis, and they'll make one dimension out of it. And the reshaping basically makes the height and width of the feature map reshaped into the batch dimension. So this will be the batch dimension that will be that is reshaped, and that will be used by the motion modeling module. And they claim that this approach makes the module operate across frames, and it enables the module to achieve motion smoothness and consistency across frames. So this motion modeling module is nothing but a vanilla temporal transformer, and containing several self attention blocks. So after the reshaping, there are several self attention blocks that are there, and they will generate basically the keys and the value parameters, like any attention mechanism. And this is across the temporal dimension. This happens across the temporal dimension. So what happens there is, let's say we are considering this attention matrix, and by reshaping, what they have done is, let's consider each column in this attention matrix as a single frame. And what they have done is reshaped this entire batch into height, into width, as a single frame. So and the video at the video data as the input to the model, as we saw in the pipeline. And so in a video there will be multiple frames. So we can consider each column or each word here in the attention matrix as a frame, as a separate frame, and there will be n frames. So they will so their self attention transformer will work on each individual frames, and it will calculate the attention scores across frames. So in this case, the attention scores will be concentrated across the diagonal, and that is because, let's say we have a cat moving, and for that video, let's say we take a frame, the third or fourth frame, and we have the cat's leg moving in the third frame, and we will see a similar movement in the fourth frame because they are consecutive frames. And that's why for consecutive frames, the attention scores will be higher. And this is what they take the advantage of mainly, and this is what they mean by their module operating across the temporal dimension. And they also add a sinusoidal positional encoding, similar to the original paper. And this is to know the position of the change or the pixel across a different across consecutive image frames. And then they have this initialized projection layer, which is the output layer of the temporal transformer. And they use this simple trick. They follow control net in using this simple trick, and which is basically because they don't want to tamper with the outputs of the pre-trained image layers, and they just want to customize their own parameters, the parameters of their motion module. That's why they use zero initializing. And if they randomly initialize those parameters, then it will basically have its own changes applied to the pre-trained image layer outputs. and they follow. So basically, they follow similar training process to the latent diffusion model, the original stable diffusion model. And there you can see the training objective down here. So there basically you have all the x naught 1 to n is nothing but the video data, that is given to the model when training. And y is nothing but the text prompts. And basically the VAs are they are not touched, they are not interfered with. So the VAs are used for the textual inversion to convert the text prompts into vector embeddings. And the ZT 1 to n is nothing but the latent codes that are produced by the module. And so they will also use something called noise latent code. So these are the latent codes that are produced. And then they will use a diffusion schedule. So in this diffusion schedule, there's the use of the noise distribution, which will have zero mean and identity variance. And this schedule, along with the alpha parameter, which is the diffusion schedule parameter, they'll use that to produce the noise latents. So and this is exactly similar to the latent diffusion model training process. And as you can see on the bottom right of the image of the slide, we can see this is the diffusion process. So in stable diffusion model, the model is predicting the noise and removing it between the time steps with the help of text prompt. So basically the text prompt, let's say in this case the text prompt is a cat setting. And so the model will remove the noise pixels and remove and add the noise pixels in relation to the text prompt. So if removing the certain noise pixel makes the image look more like a cat, then it will remove it. Or if adding it does that, then it will add the noise pixel. So similar to the diffusion process, their module addition of their module, that a temporal self-retention transformer, which is basically aware of the consecutive frames between in the video. So at the addition of their module, it's not only removing or adding noise, but it's doing that while paying attention to the consecutive frames. So that's the main change that their module introduces in the diffusion process. And that's how they train the stable diffusion model along with their motion modeling module. Some of the experiments that they have done are so basically they use the stable diffusion version 1 as the base model for training. Since then there have been many stable diffusion models, but they have used the first one. They use the WebVid 10 million text to video dataset, where each example is a small dataset, is a small video which contains multiple frames. And they mentioned that they sample each example or each video clip with a stride of 4, and then they resize and center cropped to the resolution of 256 by 256. And it's a square image, because stable diffusion requires a square image as an input. And they say that this resolution can be generalized to higher resolutions, and this is happening basically because of the reshaping of frame axis into the batch axis, which happens right here before anything is inputted to the motion modeling module. And this reshaping enables their approach to work on higher resolutions. And they mentioned that they try 3 different types of schedules. So as this training process is similar to stable diffusion, they have tried similar diffusion schedules, but a certain diffusion schedule worked better for them, which was the linear beta schedule. And yeah, we'll look at some demos. So in evaluations, they mentioned that they have used many many different types of personalized text to image models, and this is basically their comparison, because there's no set benchmark for them to evaluate their model against. So they've used personalized T2I models, such as an anime type model, a stylistic type model, a 3D cartoon model, and so on. So the style or domain of each of these personalized text to image generators will be different. So, and they in that way they compare if their approach is generalizable to all types of text to image models. And they also offer a baseline comparison against a text to video zero model, and they show through experiments that their results are more fine grained, and their results have better temporal smoothness. So as you can see at the bottom of this slide, we see the first and the third rows are the baseline results, and the second and fourth rows are their results. So they mentioned that we can see that the cup size or shape keeps changing across the frames for the baseline results, but nothing of the sort happens in their results. So the appearance and the consistency of objects in the image stays the same. And this motion module enables them to achieve this fine grained consistency and smoothness. And you can see some of the results here. So their approach of handling the motion parameters before and extracting the motion parameters from the video dataset enables their approach to distinguish between foreground and background of the results, and it adds a feeling of vividness and realism. So you can see in the right in the result on the right that the pixel change on the foreground on the subject on the girl in the foreground is entirely different than the change of pixels or motion that is happening in the foreground. So the pixels in the tree are also changing logically, and the pixels in her eyes or on her face are also changing logically. So that's what they mean by distinction between foreground and background, while and that adds to the vividness and realism of the results according to them. Yes. And the next point they mention is of appropriate motion, which is related to the temporal smoothness. And so as they use a temporal transformer, this is kind of given, but they point out that there is a assignment of appropriate motion to each pixel by their module. So their module understands input text, and it assigns appropriate motion to each pixel. So you can see that in the consecutive frame there is no drastic change between the pixels. And for example, let's say you can see the motion of the waves and how the pixels change. The each individual pixel has different motion between frames. So that's what they mean by assigning appropriate motion to each pixel. Yeah, and so in conclusion, we think that the model has been very efficient in solving the glitch problem, which is nothing but an apparent gap of information or pixels between two consecutive frames. So as we can see in the result, there are no glitches, or there are no drastic changes in any feature of the object. So that's what they were trying to solve in the first place. And they have done this in addition to achieving visually appealing and temporally smooth results. And they also mentioned that they have tried many different types of text to image models, and their approach is works for different types of such models. So we can see that the result on the left is a bit of cartoon model. The result on the right is a bit of a realistic text to image model. And similarly, these two models are also very different in their results. So their domain knowledge is different. and that's what they mean by their approach working as a general approach. And true to based text to image domain knowledge, this is this is uh, this is in terms of not generating any false or any duplicate or any irrelevant artifacts in the image. So in the right result, you can just see the snow and the cat, and you cannot see any arbitrary object there. So that's what they mean by remaining true to their to the domain knowledge of the base TOI T2I. And as they mentioned, it's cost effective. It doesn't require any data collection or any extensive GPU use. But for the cons, we also think that this needs to be evaluated a bit more, or improved a bit more. So comparison metrics is one area that the paper could improve on, because there is no benchmark comparison, similar to segmentation and other problems. This approach needs a better comparison metrics, and they also have to compare their results across with different baselines, and because they've only provided one baseline comparison. And it would be much better if they could evaluate their model deeper. So their approach depends on the base model producing realistic results. So if the base model does not produce realistic results, their model obviously fails to produce any temporally smooth or better animation videos. And as they use a slide of 4, and their resize resolution is also of 256 by 256, and their ultimate their result video size, final length of the video is set to 16 frames. So that comes out to be a result of 2 to 3 seconds. So and that's not much of a result to evaluate the temporal smoothness of the model on. So they should have had results spanning 5 or 10 seconds, so that we know that they have a robust temporal smoothness across each of the video frames. So basically, yeah, longer results. And yes, that's it. If do you have